So let's imagine that we're trying to accelerate an object faster than the speed of light. And remember that in Newtonian mechanics, there is no limit to speed. So as you are going to accelerate your velocity to infinity, what is also going to be accelerated is your momentum. And it's going to be very increasing until it's infinite. But also remember that a change in momentum is impulse. And in order to have an infinite momentum, you also need to have an infinite impulse. But this is impossible. You cannot have an infinite supply of force. It's simply just not logical. So Einstein hypothesized that there must be a speed limit. And this speed limit, he said, is the speed of light. Now, he didn't also only rely on this intuition, he proved it mathematically with the help of other scientists. I think one of them was called Minkowski. I have no idea, his name was weird. But what he did to modify the equation of momentum was include the relativistic factor, this one, which I think he called lambda. Now, let's see how this relativistic factor changes from our Newtonian mechanics. So let's say that you have an object that is moving really close to the speed of light. And let's say it is it's moving at, let's say, 0.99 of the speed of light, 99% of the speed of light. So 1 minus, and this will approximately be 1, you're going to see that this denominator as a whole is approaching, all of this is going to approach 0. And it is a rule in mathematics, and you can visualize it, that as your denominator is approaching 0, this value over here, the value of the numerator, is going to be much greater. And as a result, your momentum is going to approach infinity. So as your denominator approaches 0, your momentum will approach infinity. What this tells us is that objects moving at very high velocities have such a tremendous amount of momentum that Newtonian mechanics, this equation over here, it does not take into account. Now, if you're talking about objects that, like, in our daily life, like me walking, my speed over here relative to the speed of light, is basically nothing. So the denominator will be approximately 1, and the Newtonian equation will hold true. But let's say, for example, you're talking in an atomic accelerator where electrons are being accelerated very close to the speed of light. Now, if we follow their path of the electron beam, and we're following in Newtonian mechanics, we expect as the electron is being deflected by the magnets, it is going to deflect at a steep angle. But this is not what happens, and this has been proven experimentally. What actually happens is that the electron beam barely deflects at all. It follows this path, the one in green. And why is that? It is because objects moving close to the speed of light, as Einstein predicted, have a great momentum. And objects with great momentum resist change to their path. They're not that easy to throw off their path. You can say, as our book said, they're stiff. So when you're talking near the speed of light, you need to include the relativistic factor into your calculations. And the universe does have speed limit, and that is the speed of light.